Our last thought for section 3.4 is to go essentially over an overview of what I call our basic functions. Unfortunately, many of you like just to turn to a graphing calculator, and that's fine. But what I'm going to do is approach this in a point plotting technique. That way we kind of get a little bit more, dare I say, a little more intimate with the function. We get familiar with some important points that are actually on the function, which are going to help us in 3.5 when we move forward, or even help us do some graphing of piecewise functions or anything else a little bit later. So the first thing I've just noticed about this is we're talking functions, and I'm back to the y notation. So I apologize for that. We can call this f of x or whatever the case might be. Matter of fact, maybe I'll just do that. F of x equals k, f of x equals x, f of x equals x squared, f of x equals x cubed, and so forth and so on. Okay, so we just know that y can be replaced, right, with f of x. And what we're looking at in the first one, the name of this type of function is it's called a constant function because k is a constant value. And this function only is equal to that value depending on that. So let me give myself a value for k, like y equals 5. All right. So when y is equal to 5, if I looked at an ordered pair to graph this, right, if x was -1, y would still have to be 5. If x was 0, y would still have to be 5. If x was 1, y would still have to be 5. So it doesn't really matter what x is. This constant function tells us that the output is constantly equal to 5, constant function. So if I go plotted this, right, what we end up with is this horizontal line. So if I want a different horizontal line, I let y equal something else, like maybe y equals -2, right? And so that would basically have these 3 data points, and we'd be back down here. So depending on what k is, kind of tells us where we're going to be sketching that horizontal line for whatever value of k. So that's a classic case of what a constant function looks like. And I think we saw that a little bit in our piecewise functions a little earlier. F of x equals x. Well, again, if we approach this with a point plotting technique, right, what we end up getting, if x is -1, right, y is also going to be -1 because y is whatever x is. If x is 0, so is y. If x is 1, so is y, right? If x was -2, so is y. If x was 2, so is y. So basically, y mimics whatever x is. And when we go plot these data points, 0, 0, 1, 1, 2, 2, -1, -1, -2, -2, we end up with what's very famously known as y equals x. Okay, so it's a nice linear behavior, and those are some data points that are on that nice line. All right, so there's another very basic function, and we've actually learned how to manipulate this, right? The m causes this function to slant differently or maybe even negatively. The b causes this function to move up or down, and I'm kind of getting into 3.5, but we've actually seen some manipulations here. By the way, that does match what we learned earlier, right? You know, technically b is 0, so I have 0, 0 as my y-intercept, and the slope is 1. So up 1 over 1, up 1 over 1, up 1 over 1. So it even matches what we learned earlier. F of x equals x squared. Well, we've seen previously that an x squared usually represents a parabola, right? But what's our basic parabola look like? Well, again, let's do a little bit of point plotting. Let me throw in these nice looking values of -2, -1, 0, 1, and 2, and let's get a feel for what this function does. So if I square -2, I get 4. If I square -1, I get 1. If I square 0, I get 0. If I square 1, I get 1. And if I square 2, I get 4. So there's a heck of a lot more data points, but those are some pretty basic ones. So sketching them, we have -2, 4. We have -1, 1. We have 0, 0. We have 1, 1. And we have 2, 4. So you definitely see that basic shape of that parabola that represents an x squared graph. All right, so we're good to go. X cubed, well, again, let me go ahead and do some point plotting. Let me throw in our pretty nice famous values. If I cubed -2, we end up at -8, right? -2 times -2 times -2. If I square -1, I get -1. If I cube 0, we get 0. If I cubed 1, I get 1. And if I raise 2 to the third power, we get 8. There are many more points, but here's the biggies. So plotting these, we have -2, -8. We've got -1, -1. We've got 0, 0, 1, 1, and 2, 8. And so what you end up with is what a classic cubic graph looks like. It's kind of a nice little curvy S shape, if you would. But there's what x cubed looks like at its bare bones, right? It's with nothing else going on. We're not adding anything to it. We're not multiplying by anything. It just is what it is. So there's our basic function, along with some important points that go with it. Getting a little harder, right? Our function now is square root of x squared. Well, domain-wise, right, we can't have any negatives, right? We have to make sure that whatever there is positive. And then to help me graph, why don't I plug in some values of x that have a nice perfect square? So the square root of 0 is 0. The square root of 1 is 1. The square root of 4 is 2. And the square root of 9 is 3. So 0, 0 is on this graph. 1, 1 is on this graph. 4, 2 is on this graph. 8 and 9, 3 is on this graph. So this graph, this function, this square root function, is going to slowly keep steadily getting higher and higher and higher, but it's going to go very slowly, right? Because even 16, the square root of 16 is 4. So all the way out here, we're only equal to 4. So it eventually just keeps on increasing. That 0, right, is an important 0. There's no arrow in this case. You'll notice that in all the other cases, I'm throwing an arrow in both directions, indicating that it's going on forever, both positively and negative infinity. But the square root function, because it has a problem with negatives, right, basically starts at 0, 0. So that point is essential. What about the cubed root? Well, what we've seen as far as cubed roots is concerned, right, cubed roots actually handle negatives just fine. So their domain is still very, very robust. It's everything. We can put anything in there. And why don't we look ahead, right? What are some values of x that we can use that are nice, perfect cubes? Well, -8 is 1, right? -1 is good going, 0, 1, and let's say +8. So the cubed root of -8 is -2. The cubed root of -1 is -1. The cubed root of 0 is 0. The cubed root of 1 is 1. And the cubed root of 8 is 2. So there's at least 5 data points. Many more, but those are a nice 5. So we have -8, -2. We've got -1, -1, 0, 0, 1, 1, and then we have 8, 2. And so this graph, I think we've seen that before, looks like that. Again, it will have arrows because we can go on infinitely forever, never, never. So those are our 6 of our basic functions. I believe we've seen many of these before. We've worked a lot with lines and quadratics. We've seen some cubics and square roots and cube roots, but there's basically kind of an intimate view of them, and I recommend you guys maybe take this off to the side, put your graphing calculators away, and do some point plotting yourself. All right, that way you're kind of like, again, I'll use the word intimate. You get really familiar with what y equals x looks like, what y equals x squared looks like, what y equals x cubed looks like. What is a square root graph supposed to look like? What does a cube root of x graph look like? Because the more you're familiar with that, the better you're going to be with 3.5 and beyond material. So please make sure, just don't turn to your graphing calculator and plug it in and just have this, graph sitting in front of you. Try to deeply understand what's happening and maybe redo some of the things that I did. We actually have some more basic functions to look at, but we're 9 minutes into this, so I'm going to use those. I'm going to look at those in another video.